All right. Well, thanks for staying to the almost last talk. First of all, I would really like to thank you for the invitation to this wonderful workshop. I mean, it has been a pleasurable series, and so I thought I'd give you a little bit of an update specifically about things that happened because of this workshop series. I mean, there were very interesting discussions we had, for example, in Tel Aviv. And so I thought it may be interesting to somewhat update you on what has come from this in some sense. So I'll specifically thank all these people, but in particular, notice that the clicker is not working right now. Anyways, no, it's not on. Good. Let's see. All right, fine. So in any case, I want to tell you two short stories today. One is about quantum oscillations as a probe of highly metallic topological systems. So we heard a lot about isolated cones and very well-defined Weil and Dirac semimetals. But what if we have a Dirac semimetal, say, coexisting with large Schrödinger-like bands? Can we then do something? Does something of that topology survive? Or is it completely lost? And the second part goes about generation of currents and current beams by using a controlled version of current jetting. Of course, current jetting in this field of gapless topological phases has attracted a lot of attention as a potential source of worry when we discuss longitudinal and negative magnetoresistances. And this is true, and it is a very classical magnetotransport phenomenon, but maybe we can turn it around and use it for something and do new, cool, maybe topological physics with it. Okay. So very generally speaking, the main point is, let's say we have two Fermi surfaces like this, or band structures like this, with a Weil or Dirac point, we have a trivial pocket, right? And we put our chemical potential somewhere up here, and so that the Fermi surfaces are the same, the Fermi velocities are the same, they look very, very similar. Now, of course, I can do ARPAs or some local spectroscopic probe to distinguish these two phases. But is there something I can do to measure macroscopic phases, or to measure, let's say, macroscopic physical observables like transport or magnetization to distinguish between these different phases? That is somewhat the question that we wanted to pursue with this. And one thing that has been discussed quite a bit is the use of quantum oscillation phases. And this is something that happened, for me at least, I got very interested in this in the last workshop in Tel Aviv, where Aris Alexandrinata, working with Glatzman, has brought forward a rather stringent theory on how you can identify and classify phase offsets to the Onsager quantization. So if you look at the problem, then, oh, well, that's too fancy right now, okay. So if you look at the problem of electrons in a magnetic field, then you could write down some sort of an Onsager quantization rule, which basically takes the area of the orbit in k-space, whatever it encloses as it is in the Landau level, and you quantize the flux through this box as being an integer number plus some offset phase factor. And of course, now this is a very intuitive picture that you orbit your electron around a topological defect, so it picks up a geometric phase, so you would expect an additional phase. And this seems to work rather well in graphene, so here this is actually one of the first works ever in graphene, where they compared graphene and thin graphite, which has the same Fermi velocities, the same size of the Fermi surfaces, same slope of a plot, where you would plot the position of the nth Landau level versus the index n of the Landau level. You get a straight line, and that's your frequency, but then also you find that there's a clear offset of this. So you could do some simple math and say, okay, I have a harmonic oscillator essentially, my phase term should be a half. Okay, now I have the additional geometric phase of another half, and I get 0. That is, of course, oversimplifying a lot. What you really need to be doing is to compute the Landau level spectrum of the Dirac equation, and then you would find that this phase should be 0. But very generally speaking, this is the logic, and it really doesn't work. It does not hold. And one of the things that I find most interesting in this concept when discussing various phases is that actually the very first metal where ever quantum oscillations have been observed, which is bismuth, simply because it has a very low quantum level and you can make it extraordinarily clean very easily. So this is where actually quantum oscillations have been discovered. The very first already had a pi phase shift. So if you read the original work, what they found is that for bismuth, good agreement was found with a theoretical formula, except that the signs of the fundamentals and all odd harmonics had to be reversed. This was a time where theory and experiment really worked together quantitatively in a sense that they actually cared. Nowadays we would just say, oh, look, it oscillates, I want it to oscillate, it's done. Here they didn't, right? And that's quite interesting. There is a pi phase shift in bismuth, and bismuth is, as we heard, it's a very interesting material. It may have topological aspects in terms of being a Hoti, but certainly it's not a Dirac semi-metal. These pockets do not enclose any topological defects, so there is no Berry phase contribution to these oscillations. And it turns out that this is entirely driven by this extremely strong spin-orbit coupling in this material that fakes a topological response if you believe this, this phase offset. So what are the main issues here? And there are two things that we really need to keep in mind when discussing these things. And the first one I already alluded to with the bismuth, that there are more corrections to the phase than just Berry. If it was only Berry, it's nice that you just look at the difference and you're done. There are more. And the other one is that the degeneracies are really a problem. You have to remember that Lifshitz-Kosevic is done in a time where we try to understand the Fermi surface of aluminum, copper, right? So there, you basically, if you have a, let's say, centrosymmetric metal that's non-magnetic, then the only symmetries, or the only degeneracy you have is a twofold degeneracy due to spin. So that gives you a twofold degenerate state, and those degeneracies you can trivially take out of Lifshitz-Kosevic. This is what people call the spin damping factor. It's basically summing over two degenerate orbits. You get different phases for the different spins, and you can pull this out, and you eliminate this nasty phase of the Zeeman term from the Lifshitz-Kosevic equation, and you call this just the spin damping factor. Here we have more. So what does this mean? The first part is about the degeneracy of problems, or what adds to your phase. So you start with a phase of pi, which is, if you pull it out, this is this 1/2. That's the harmonic oscillator, if you want, and there is more complete theory on this, basically putting this into the topology of the orbit itself. But what we consider is we have a wave packet that sits somewhere at k and r, and now as we apply a magnetic field, it's forced to rotate around whatever Fermi surface it has. And it has been shown now that there basically are 3 contributions up to the expansion on h bar that will add to this problem. One is Berry's phase. Okay, I could have some geometric phase as I evolve around this. The other two are more subtle in some sense. The rotation phase is basically a center of mass self-rotation of this wave packet, which is something that is allowed if you have multiple bands to which you can do virtual transitions. So basically, this packet can, while it spins around the center, it can also spin around itself. That will give it some additional phases. And then there's the Zeeman phase. That's just the spin phase that will add to yet another degeneracy term. And in particular, if you have strong spin-orbit coupling, this can be mixed up together in a very non-trivial way. So we really need to identify all of these phases before we can say anything about Berry. And so in bismuth, actually, it's that Berry is 0, but this here is pi. That's what happens. Okay, good. Degeneracies, well, we know, as we heard, for example, on all of the multifold degenerate orbits, 4-fold, 6-fold degenerate fermions, there can be high degrees of degeneracy. And additionally, we can have systems where we have copies of these Fermi surfaces due to the crystalline symmetry, because our topological points usually sit on low symmetry points, or not on the gamma points, so you get all of these copies. If you think, for example, about wild semimetals that are inversion symmetry broken, those that we mostly have in the lab, they have 24 Weil nodes sitting in all directions. So you will have high degrees of degeneracies that you need to take into account in this problem. So what happens now is that basically for every orbit, you will get a different phase factor. You can't say that they're all the same. They may have relations by symmetry, but they will be a priori different, right? So mathematically speaking, the problem is that your oscillatory component is a sum of lots of signs of degenerate orbits. Degenerate orbit means that all of the areas is the same, so there will be oscillators that oscillate at the same frequency. That's nice, but they will all have phase offsets which are different. Experimentally, I can only measure one phase. I see my resistance oscillates, it has an amplitude and it has a phase, frequency. That's what I can measure. right? So I have to somewhat reduce an overspecified problem into my single thing that I can measure. And that's the problem, that's a fundamental problem of the Fermi, of this lambda plot analysis, which inherently assumes that all of these lambda are the same. Then of course you can do that and you can identify lambda with theta. But in general you can't. So if you really want to do this, and it's tedious, and I will show you how it could be done, then you need to look back into the derivation of the equations itself before you extract the spin damping term. So you have to sum over all of the degeneracies, but then also over all of the harmonics. And it's really the higher harmonic processes that save you. The first harmonic is the wave packet going around and interfering with itself. But there's of course also higher order processes going around twice, 3 times, 4 times, and so on. And this now has a key component here, namely that the harmonic index basically multiplies the phase that you see. So basically now, if you go around the same, whatever your band structure is, 5 times, you will pick this phase difference up 5 times. And that now gives you additional equations that can constrain your unknowns. This is the key point here. So if I can measure multiple harmonics, I will get multiple equations that constrain my lambda. And then I can solve the set of equations. So why is this at all relevant? Okay, if you only care about fermions and you want to look at them with ARPAS, then forget everything I'm telling you about, because you have your thing, you look at it, it's done. But there are many, many systems in which it is much more difficult. And one system I want to point you out particularly is this compound, lanthanum, rhodium, indium 5. It's a tetragonal crystal. There's lanthanum here, there's indium planes, there's 2 independent indium sites, and then there's a rhodium plane in here. It is a very, very large bandwidth metal, has very high charge carrier density. And in particular, or one of the interesting things about it is that it also has a Dirac point sitting down here. So it's a Dirac point node semi-metal. This has been proposed before, and we basically revisited the problem, but there were some differences in the interpretation. Key point is it is a Dirac semi-metal, but there is, or metal, I guess. I mean, I don't actually know the bandwidth. It's 3 or 4 electron volts. It's a huge band. And about 0.1% of these electrons sit in the Dirac Fermi surface. Irrelevant number, right? In principle, the question now is this still a topological semi-metal or not, in terms of the macroscopic observables, right? Can I think about this as topological or not? Band structure says yes. It's very interesting that also the macroscopic observables say yes. So it's completely non-magnetic. Lanthanum is in a 4f0 state. There is nothing magnetic about this whatsoever. So if you still measure the magnetization as a function of magnetic field, you see gigantic quantum oscillations in this that correspond to a frequency, so here's the quantum limit of about 7 Tesla, that correspond to this tiny, tiny pocket. And then after this hits the quantum limit, you get a very, very large enhancement of the magnetization beyond this. So this only comes from this 0.1% of all electrons. It's a very, very strange magnetic response of a metal that you wouldn't expect a priori, because, well, basically no of the electrons contribute to this. To give you an impression about the Fermi surface, you could compute. There are many, many bands in here. The Fermi surface generally looks very messy. If you want to find the Dirac point, you have to take the central object here, the red band, which leads to this crazy 3 stuck into each other tubes. And then you have to look down into the tube. And if you do that, then you will find that there is the Dirac point in here. So it's a tiny ball that sits in that tube. Actually, one of the reasons why it was missed before, because from the outside you can't see it. It really sits inside of the object. Right? Okay, so this is the thing. So I'm talking about these 5 pixels that you basically can see here. Those determine the transport, those determine the magnetization, those determine the quantum oscillations, and all of these don't. And these are the topological. Now, of course, it would be interesting to, the speculation will be clear, right? Okay, good, I have Dirac Fermions, they're very high velocities. I have topological protection from backscattering, which doesn't really work in 3D, but let's ignore that and say, okay, well, this is why we have this, right? It's a very strange problem. Okay, so now we measure quantum oscillations of this. Here you see a measurement that we did. This resistivity is a function of magnetic field. Again, there are huge modulations at very low fields of only this pocket, right? Remember, there are plenty of other bands around. They also give quantum oscillations, and this is the fuzz around the main oscillation, right? All of this, these are the 10 to the 4 times more electrons. The rest is this. Now you can already clearly see that this is not very sinusoidal, so there's higher harmonics. So you do a higher harmonic decomposition, and now you have the key information about the topology. You have the relative amplitudes of these 3 harmonics, and also the relative phases of the 3 harmonics. And this is what you can now use to recompute the Lifshitz-Kosevic for the given symmetries of the system. And if you do that, then you can find that actually all your lambda are hidden in amplitude ratios like this for the 3D Dirac semi-metal. So if you divide the amplitudes of the first harmonic over the rth harmonic, you will find a term that's cosine divided by cosine of r of lambda. And this you can now solve. You can solve this self-consistently for all of them, and then you will find that there is a lambda of very, very, very close to pi. This has nothing to do with the phase of the primary oscillation. That's irrelevant. It's a phase, it's a ratio of the amplitudes of the first to the rth harmonic. That gives you pi. It's not quite pi. And the differences here is that, again, there are 3 main components. Turns out that spin-orbit coupling gives you something on the order of 0.07 pi. So I'm not showing this because actually it gives you ridiculously close to pi. But it is a very weak compound here, and the spin factor also is relatively weak. So this is now what you need to show next. I don't want to walk you through all of that, but the point is here, with an analysis like this, you can maybe not prove, but have very strong evidence for a Dirac pocket, even though you're stuck in huge metallic bands. And a key point there is that the analysis relies on the fact of the smallness of the Hall effect. So the huge metallic bands actually help you a lot. So what we're now doing, because they quench your Hall effect, or reduce the Hall constant. So what we're now doing is to basically show that in this situation you can find a very pure current jetting free version of the chiral anomaly. Because there is no magnetotransport anisotropy induced by the magnetic fields, because the entire metallic bands actually screen the anisotropy that you would just get from the small semi-metallic bands. So this, I think, is an interesting direction. I wanted to show this to you because all of this basically has started in Tel Aviv. And now I would like to go to the second point, which also started in Tel Aviv, but in a different type of constellation of discussion, mostly with Adi, on the identification of long-range topologically non-trivial currents due to the Fermi arc, or basically this Fermi-type orbit. All right, so let me remind you of this. So let's say you take a slab of a Dirac or Weil semi-metal. You have your Fermi arc, so this would be a Weil system. Let's say we just have 2 nodes and some Fermi arcs here. You take a slab on the bottom and top surface. Now you apply a magnetic field perpendicular to this surface. You Landau quantize your bulk spectrum, and then you use the 0th order, the 0th Landau level, or the chiral bulk mode to connect between these nodes, forming this closed loop, which then could show quantum oscillations in principle. I mean, this was Ashwin's original proposal, which made me go to Berkeley and do this experiment. And in fact, we can find evidence for this in cadmium arsenide, but there are additional quantum oscillation frequencies when you make it very small, or basically when you make this slab very thin, so that the 2 surfaces could actually talk to each other in a quantum coherent way. But this is now this process, and that started Adi Yuval and Erez basically to think about the semi-classical versions of this. So let me walk you through this proposal real quick. Let's say you have a cube of copper with 2 very closely spaced contacts here. Then you know that you solve Laplace equation and you get a very local current profile here. So if you measure the voltage, let's say down here, there will be basically 0 voltage. It will be very, very small, and if at all you see something, it's positive. If you do this in a topological semi-metal, this is what they get. It's a very delocalized current plume that focuses in the presence of magnetic field that focuses a shadow current onto the other side. The idea here is, let's say you have this wild type orbit, then you apply an electric field, you will populate states in this Fermi arc, you will have bulk transport and Fermi arc transport. Now you apply a magnetic field, the Lorentz force will force these states to slide around here and then populate the shadow arc on the other side. That's essentially what happens. So you drive current this way on the top, and by chirality locking, you will drive current into the other way on the bottom of the surface. Yeah? Yeah. Okay. All right. So then this. So here you see a structure from cadmium arsenide. Basically, it's supposed to resemble this. That's what I do, cut stuff with the focused ion beam to make these types of experiments. So now we want to source current here, measure voltage on the other side, and yeah, we expect to see nothing until the Addy effect hits in and we see our negative magnetoresistance. Good, or negative signal on the other side. This is what we actually see. So now we apply a magnetic field, let's say in this direction, in the plane, and then we rotate away from this direction, but all in plane fields. So we see this signature on the other side of the device. Basically no voltage if it's far away. Then there's a strong negative dip, large positive dip, strong negative dip, and so on. Great, non-local transport, we're done, right? There is even a voltage inversion, so you get negative voltages on the other side. So that's somewhat non-trivial to get. If your current flows this way here, and now you get an oppositely charged voltage on the other side, that's not that easy to get. And well, of course, so there's then the origin topological effect would do this, and then something else kicks in here, and you get this. But if you actually think about the problem, there is something missing in here, and what's missing is the huge magnetic field-induced anisotropy in these systems. Right? It's a semi-metal, after all, has a very large Hall effect, and if you apply the magnetic field in one direction, you will basically localize the electronic motion perpendicular to this thing, while parallel to it, it can still move. This is what's current jetting, essentially. So if you plot the conductivity, for example, as a function of magnetic field, then the conductivity along the magnetic field will slightly increase and have huge quantum oscillations, while the conductivity perpendicular to it will drop. This is just magnetic field localization because you spool the electrons and you basically stop them from propagating perpendicular to the magnetic field. So actually these devices in fields of 14 Tesla, they're extremely anisotropic. 700 or so is the anisotropy. Even though you start out with something that's pseudo-cubic and essentially is an isotropic conductor. You can compute now what happens. You have 2 point-like current injections here, and then you increase the magnetic field, and now your initially local thing will become completely delocalized. For absolutely classical reasons, or not classical reasons, but non-topological reasons. Of course, we're not the first to point this out. There's current jetting has plagued this field for the last 50 years. Will probably plague it for the next 50 years as well. Main point is that you get somewhat of inhomogeneous current injections. You apply magnetic fields, which will strongly distort your current patterns. And then if you put just some voltage tabs here and interpret this as a homogeneous flow, you will get crazy experiments, crazy results. And why this happens in practice is that this is how we do our measurements. We grow some crystals, we slop on some silver paint here, or silver epoxy, but essentially this will be some tiny particles, and depending on your surface, some of them may touch, and some of them may give you point-like contacts, and there you go. You have a very inhomogeneous injection into a highly anisotropic metal, and therefore you get very, very crazy current patterns. Okay, so if you do the simulation, then you could actually completely understand our pattern here. So if we go, for example, to this angle where we see negative, there we start our current here. The current forms these beams, but now we shoot this beam diagonally into the other contact. So here you have 0 voltage, here you have positive voltage, so if you subtract, you get something negative. On the peak, you shoot them straight into each other, so you get a high voltage. And if you go to some very wide angle, you just shoot them into the sidewall and you get nothing if you measure the difference. This is where it comes from, and we can quantitatively match this. Okay, so on one side we could say it looks very bad for this proposal of topological non-local transport, because you will have to actually self-consistently formulate a theory of transport that takes this into account. On the other hand, it's actually quite interesting. We can take a non-trivial material, generate these beams, and shoot them around. Right? So what happens with this, right? Can we now start to think about probing, for example, the topology of the system by doing these experiments? And we could also have multiple devices of multiple contacts and play these games that really you mathematically capture the entire profile. So this is what you can do. And as far as I know, this is the first experiment where you have quantitative structural and, let's say, current path control over current jetting. Here, current jetting does not appear as some artifact. Here it appears by design, and you can shape it in every way you want, and you will get these current jetting patches. So that's what I find quite interesting. All right, so here are my conclusions, but what I really wanted to conclude, because we are here in a more of a discussive thing, I think there is a disconnect right now between the experimental and the theoretical community. With the theoretical community really focusing on minimal models and what happens in the perfect world, while the experimental community looks for these signatures in hellishly complex materials. If you think of any inversion symmetry broken wire semi-metal, it's so bad, you would, even without topology, have no chance of computing Boltzmann transport or anything in them. These are 30 or more crazily shaped Fermi surfaces. We have forgotten a lot what happens in simple potassium and other semi-metallic systems, and we barely understand these materials without topology. So what I really think we need to somewhat do is formulate a self-consistent theory that takes into account the experimental situation of these materials, of realistic materials, and topology. And I think that's where we'll find really cool new effects. What does the chiral anomaly, for example, do in my current beam situation? There's no more electric field that is just following between my contacts. It becomes very delocalized. So is that maybe a way that we can actually probe this? All right, thank you for your attention.
Thank you, Philip. Are there any questions? Any hands going up?
So just to make sure I have understood correctly, so if you would do this experiment with copper or like a normal metal, you would get the same result for current jetting?
No.
Like an isotropic metal, like, some with anisotropic conductivity.
So the point is that the anisotropy of this is entirely field-induced. And if you have this in copper, you would never get this. There are two reasons for this. One is that the cyclotron radius will be too big, or basically the scattering matrix elements of these material of copper, let's say, are too high. So you're still in a hopping, inter-Landau level hopping assisted type transport. And the other point is that you will have a very, very small Hall effect in a good metal. And this is a key point because the actual solution that leads to this, I don't know where I have this picture, but it's basically this spiral, right? And this spiral is an effect of the out-of-plane Hall effect. You need the out-of-plane Hall to swirl this around, and this you don't have in copper.
Okay, maybe I can reformulate my question. Like, are the arcs doing anything here, or is this, because this, as far as you explained, is purely classical, right?
Exactly right.
So that's why I said copper, but maybe I should have said. Is it related to Fermi arcs at all, or
no?
It's probably not, right?
This is an entirely semi-classical phenomenon that you will find in any semi-metal. The key thing is, of course, now this picture explains rather well what we see. So, okay, this will be the dominant effect. But on the other hand, what this will do is it will lead to very, very non-trivial electric field distributions, and in particular also E.B distributions in this thing. So really what I think needs to be done is that we need to have some sort of a self-consistent solution where next you will iterate a topological change of the chiral anomaly effect-induced conductivity, and then redo the semi-classical version and so on until this converges. And this might be interesting because maybe we could see beam deformations, maybe we could see differences to the semi-classics. This is where I think topology could actually become observable. But really what we need is to look for features on the scale of the difference of the data and the model. There, right? So these will be, let's say, 10% at best modulations.
Thanks. I have one question regarding your first point with the small Dirac point in the metallic system.
Yeah.
Because it seemed to be a bit away from the Fermi level. I'm just wondering if you can tell me, like, how much can such crossings be away from the Fermi level that we can pick up some signatures, and when does it become too messy?
Well, this is in some sense the discussion that we had about how bad we are at doing DFT, right?
Yeah.
So if you just take this for face value, and let's see, yeah, no, that's probably still it. So if you take DFT as face value here, then it's very far away from the Fermi level. That's not what we see. So we need to, if we want to make our pocket match with the experiment, we actually need to shift the chemical potential down here. You can see this also on the plots of the Fermi surface. This is the Fermi surface at the DFT level of the Fermi energy, where it actually is already merged with the bands. And then if you go down to this node, it starts to detach, but it's still attached at this level. We have to be somewhat here that we actually get anything in the 100 Tesla range or so.
But I have another question.
That happens. So it's probably just.
Okay, but okay, sorry, but that confuses me more. How can you then be sure that this is actually the node, or you don't have like a different very point like Fermi surface somewhere in a very different band structure?
Well, if you believe any of the analysis I've shown you, then that tells you that there's a Dirac point in them, and that's the only Dirac point in this structure.
Okay, but like if the DFT would be completely different, it could also be some.
Oh yeah, yeah. I mean, if we go to the statement that DFT is completely wrong, and that the Dirac node sits here, yeah, sure. Then I have no idea. Okay. That's right. But this is a general problem in here because we have 7 elements in the room itself. We have lanthanum, where I would say we know nothing really about the pseudopotentials. And now we try to compute this band structure, which is heavily multiband, and we have to shift these up and down around. I would probably be surprised if it's completely wrong. And you also need some high symmetry line for the Dirac node to be stabilized, which in this case is the 4-fold rotational symmetry of this object. So it's probably not that bad, but it's bad.
But do you see any evidence for the other pockets you should cross if the Fermi level would be down there? Or?
Yes, but the problem is that there are very, very many, and we see very, very many oscillations. So if theory predicts you 32 oscillations, I find 18, I will always find a match, right?
Yeah.
So,
okay.
Yes, I would say yes. The coarse features are there. There's something that's somewhat cylindrical, there's something that's somewhat 3D, that we see, but quantitatively matching the details of these things, like where these little horns are here, and
Thanks.
yeah.
So I'm curious. So in the original proposal by Sid and Andy Stern, so that basically I can apply AC current. Maybe on the side you can detect light instead of light emission instead of current. So I'm curious, like in experiment, in reality, how fast can you switch?
No. So Adi has 2 proposals in there. One is the AC and one is the DC. We're looking for DC.
Yeah.
There's nothing AC in here.
Yeah, I know. I'm just
But
curious.
also the AC wouldn't work. The AC will suffer from the exact same thing, because also your optical conductivity tensor will become highly, highly anisotropic.
Okay, we can discuss it later, but I'm curious, in reality, how fast can you switch the current direction?
Oh, you mean what frequency I can apply?
Yeah.
Well, what people can do is gigahertz. What I can do is not gigahertz. I mean, the equipment I have is up to, let's say, 10, 20 kilohertz. It's a DC, I'm running a DC transport lab, right? But in all of these calculations, basically the magnetoresistance anisotropy is missing. So the same effect will also screw up this. It's something similar to these Asbel-Kana type oscillations that he had proposed, where you get some resonant transmission through a slab. This also lacks this, so it will not work. 5 minutes.
More questions? Okay, well, let's Phillip. Thank you again.